Welcome to Academic Diaries class. Quick one. In this question they said this is the circuit, and in this question they are asking us to find current in the 0.1 ohm resistor using Norton's theorem. Now to get this question, all I've told you before that once you see a question given and they say Norton's theorem, it's still the same thing as nodal analysis. The only thing they want you to prove there is that you apply Norton's law by saying that whatever resistor they are talking about, you short circuit it to become a wire. And in the end, you remember that Norton's theorem states that in a linear circuit, that every resistor and every current will become a parallel current. A parallel current that is in parallel with the load resistor and the Norton's resistor. So if that be the case, let's apply it. This 0.1 ohm resistor becomes short circuited, so it becomes a wire. So if it becomes a wire, let's be fast. If this becomes a wire, then the next thing is to apply the principle of nodal analysis. So applying principle of nodal analysis is to ask myself, how many nodes do I have here? Node simply means junction. Every point that current enters a wire, you can say it can be 2 or more. When it's 3 or more, it's not a junction, and the junction is still a node. So if I know that, let's check for the nodes. Anywhere I meet currents, a circuit, a source, that's where the node starts, and that's also where it stops. So if I'm going, you see that at this point I meet another source, so current is entering this switch. And notice that as I moved from this end of 5 amperes to 2 amperes, as I moved, if you come down here, you see that there is a wire connected to a resistor. Moving down as well, there is a wire connected to a resistor. This is 0.5 ohms and this is 0.4 ohms. So this forms what we call the bridge, or you say a node. I want to use node. So this forms your node because the wire, I know that you will say, yes, this is junction right here, this is a junction right here. Let's say I call this V1. This is also V1. These are junctions, and we know that according to Kirchhoff's, current entering junction and leaving junction is equals to 0. So if I know that, it is determined by how much source, by source I mean is an ammeter, switch, resistor. So wherever I have that source, that's where my node starts, and wherever I get it when I must have started, that's where it ends. So this is for this particular node. So this is node 1. We'll call this node 1. So now let's analyze node 2. If you come down, you look at this now, you see that on this end I'm having something like this, starting with the same source. See that I'm having something down here that looks like what is up, but just that this one is downwards. So you see that you still meet the resistor, you still meet your resistor, the same resistor. This is 0.5 ohms and this is 0.4 ohms. Now you see that they've given us the direction. The 5 amp is moving this way, the 2 amp is moving this way, ampere is moving this way. But you can now apply the rule of nodal analysis. So the first one I'm giving you on this question is simply current on the inside will always move from node 1 to node 2. So it simply means that if I have a current inside this particular resistor, that current will move downwards, and this current as well will move downwards. So why is it moving downwards? Because we always establish a point on the ground, that is a voltage on the ground, which is our reference. So if this is the voltage on the ground, we can see that this voltage on the ground, we are establishing it in node 2. So that means that node 2 becomes 0. The voltage on node 2 becomes 0. So let's say this is V2 and let's say this is V2. Everything here is V2. Everything here is V2. So our V2 in this question is equals to 0. And that is why we say that whenever you have two nodes, whenever you do this analysis and you find out that what you have is two nodes, the equation that you will be using for that particular question will just be one equation. If you find three nodes, the equation you'll be using is just two equations. If you find four nodes, the equation you'll be using is just three nodes. Three nodes equation. While if you find five nodes, the equation you'll be using is just four nodes equation. Reason is that the last one is always the ground. The one that is supposed to make it five equations is on the ground, and there's no need finding the equation for something that is having a voltage of 0. So if I know that, it simply means that this analysis that I've done, obeying the principle that current must travel from a particular node, the first node to the second one, from the second one to the third one, from the third one to the fourth one, and all of it are always pointing to go to the ground. That is moving from a higher potential to a point of lower potential. So if I've noted that this is the draft we have for this, so let's say we call this one, the first one, I1, current 1, call this current 2. It's the same current that is here. It's the same current that is here. So if I come and put it on our measure diagram, you can see that this is going to be this way. So this is that I1, this is that I2, and the direction is this way. So now that I've noted this, it's now time to solve. We'll have only one equation for this, reason being that this is node 2, and this node 2, the voltage is on the ground, our reference. So our V2 is equals to 0. So let's solve. So applying Kirchhoff's law on the first one. So I want to clean this. You've noted it. So applying Kirchhoff's law, current entering. So this current is entering the first node. 5 amps is entering the first node. This current is leaving the first node to the second node, going to the ground. So minus I1, anything that is leaving a node is minus. This one is also leaving the node, minus I2. Now this particular one is entering the node, the first node, so it's going to be plus 2a. And applying Kirchhoff's theorem, everything is going to be equals to 0. So now that you have this, you now solve. This is the only equation you will use to solve. Reason being that I told you, if you find out that the circuit given has two nodes, you are going to have one equation. If you find out that it has three nodes, you're going to have two equations. If you find out that it has 4 nodes, you're going to have 3 equations, because the fourth one is your ground. You don't have to do equation for something that is on the ground. The voltage there is equals to 0 automatically. So if I've noted this, so let's check the current in I1. So let me first draft it out. I1, let's check. Notice that I1, if this is V1 and this is V2, everything here is V1 and this is V2. I1 is in between V1 and V2. So I1 is simply equals to V1 minus V2. It moves from higher potential. Assuming this arrow is up, like this, it will be V2 minus V1. Anywhere you see your current going, any direction you see your current going, know that the voltage there is highest, and where it's going to is the lower potential. So if I know that this is going to be V1 over V2, V1 minus V2, so always use potential difference instead of just voltage where you are treating nodal analysis. Now if I've noted that, I will now come and say, remember that current is voltage over resistance now. So I will now come and say the resistor in between is 0.5. So all over the resistor in between, which is 0.5. So to find I2, let's use the same principle. To find I2 will be the same thing as saying, notice that this is V1 here, this is V2. So check it now. V1 that is here and V2 in between is the same resistance. So this is going to be the same thing as saying V1 minus V2 all over. What is the resistance in between? 0.4. 0.4. So if you check it, you see that this is the same thing as V2 is 0. V2 is 0. So this is the same thing as saying V1 over 0.5. This is V1 over 0.4. So I'm just going to repeat it. So my V5A minus V1 over 0.4 over 0.5 minus V1 over what are you doing? Yes, is it 0.5? This 0.5 they gave us? Yes, 0.5. So then over 0.4. Yes, so plus 2a equals to 0. Plus 2a equals to 0. So now that you've noted this, I want to clean this so that I'll have more space to solve this question. Okay, so let's do the punch. You can see very well that this is 5a and 2a. 5 plus 2, 5a, 2a is 7 ampere minus V1 minus V1, 0.5, 0.4. This is the sentinel saying, this is automatically the sentinel, but let's equals to 0. Let's just solve. Let's just use principle of LCM. So this is 0.5 times 0.4, 0.5 times 0.4. Hope you're still recording. Okay. 0.5 times 0.4 is 0.2. 0.2. So I have 0.2. So if 0.2 is here, if you come say it will become 0.2 times, but I've just done crossover, but let's just continue. So 0.2 times 7 is 1.4. 1.4 minus, this is 0.4 V1 minus 0.5 V1 equals to 0. So let's do this. So it's simply the same thing as saying, you know that this will come and times this, it becomes 0. So it's the same thing as saying 1.4 minus, this one is carrying V1, so 0.4 plus 0.5, so minus 0.9 V1 equals to 0. Yes, now this will come and time. So this can choose to cross equality sign. So we have minus 0.9 V1 equals to minus 1.4. So cancel, that is divide by minus. So V1 will be equals to 1.4 all over 0.9. So 1.4 divided by 0.9. So that is V1 is equals to 1.556. So let's do it 556, which is approximately 1.6 volts. That is for V1. Now for V2, yes, so for V2 to get okay, V2 is 0 already, so we have now that V1 is equals to 1.6 volts and V2 is equals to 0. So if I know that, all I need to do now, remember when we started there was a current here, they now asked us to find what is going to happen. And first of all, that current that we short circuited is supposed to be IN, Norton's current. So if this moved this way, and this one moved this way, and this one is moving this way, so it's more like saying current is coming here, another current is coming here, then these ones are going outside. So this one is going here, this one is going here. That means Norton's current is in series. This Norton's current that is here is going to be in series, but this one is bigger than this. So let's say we put this here. We don't really know, but let's put it, we are using the idea that since is outside is in series. So this series circuit, now this series, this one is coming here, this is coming here. So this series circuit, when it gets to this point, it will have to enter here and still continue. And this particular one, when it gets here, it will have to enter here and still continue. So what it means is that to find the Norton's current now will simply be the same thing as saying what is the current in I1. So remember that I1 is V1 over 0.5. So I1 equals to 1.6 over 0.5. So I1 is equals to, let's do it, 1.6 divided by 0.5, which is 3.2. Okay. Now I2 is equals to V1 over 0.4. So that is 1.6 over 0.4. Wow. So equals to 4. I2 is equals to 4 amps. This one is 3.2 amps. Okay. So that means this is going to be 3.2 amps. This is going to be 4 amps. So now, if this is entering here 5 amps, as it enters here, 5 amps that entered here will minus these 5 amps that entered here. The current that entered here will simply be equals to, guys, this is 5 amp entering here. To get the current that will continue here is simply going to be 5 that entered here minus the one that is here, 3.2. So I'll have, let's do it now. Guys, I know that 5 entered here, there is 3.2 here. The one that will continue here is going to be 5, or you can simply say current entering, that is on this. So 5, yes, then this one is leaving, minus I1 that is leaving is equals to what is entering on this IN. So that is the sentence as saying 5 minus 3.2 equals to IN. So 5 minus 3.2 equals to 1.8 amps. Now let's check again. On this one, what is entering here is 2 amps and what is leaving is 4 amps. Then what will continue will be equals to these 2 minus what is leaving here. That is what will continue here. So that means 2 amps, 2 minus I2 is also equals to IN. So 2 minus 4 is equals to minus 2. And remember, this particular 1.8 that I got is approximately 2 amps. So this one is 2 amps as well, minus 2 amps. Now what it means is that current is moving, 2 amps is entering here and negative 2 amps is also entering here. Reason is to show you that what you have here is higher potential and what you have here is lower potential. And because they are in series, remember I told you that current in series are equal. Whatever current you have for a series circuit is the same current. So for that reason, IN is simply equals to 2 amps. IN is simply equals to 2 amps. That's the answer. IN is simply 2 amps. So the current in that ohms resistor we removed for Norton's is 2 amps. So once I've gotten this, if I want to now draw the Norton circuit, all I need to do, somebody might want to tell me, why didn't you come and do it like this and do it like this and then add up? I can't add up like I did in the other case because this is 2 nodes that I have, and these 2 nodes that I have, whatever current is flowing in series is the same current. You don't do series twice. So all I just need to do is to apply the principle of what is entering and what is leaving. What is entering and what is leaving will be the same for what is in series. So So applying the Norton circuit, I'll simply remember that Norton circuit is always going to be in parallel, where I have the current IN, which is 2 amps, to be in series with the Rn, which is Norton's resistance, and then to be in parallel in series and then in parallel. So it's the opposite of Thevenin. Assuming it's Thevenin, you have voltage in series with the Norton's resistor, with the Thevenin's resistor and then load resistor in series for Thevenin. But for Norton, it's always going to be current in parallel with Norton's resistance and then load resistance. So this is going to be RL. So now notice the RL, the load, is that resistor we removed here, which is what? 0.1 ohm. That is the load, 0.1 ohm. So to find this Rn, in order to complete this, all I need to do is to go back to the equation. That place I removed, from that place I removed that particular, that I short circuited the resistor. All I need to do is to make it an open circuit. So instead of short circuiting it now, I make it an open circuit. The advantage of this class is that those of you in engineering that are doing electrical engineering, as you progress, you will still be doing all these. This is what we call circuit diagram. So as you progress in level, it is still part of your curriculum. So you see, you extend this. This is the open circuit. Extend this open circuit. So this is going to be the Rn. You find the Rn, and this Rn is always the same thing with Thevenin, or you say RTH, Thevenin's resistance. So now that I have this, let me remove all these things. I don't want to draw the diagram twice. We already know what the current is. How we got it. So now that I have this 0.4 ohms, and then everything that is a current, when you are finding the resistance, everything that is a current, that is a given current, should be short circuited, so it turns into a wire. If you have voltage, the same thing, it turns into a wire. So that means all I have is just the 0.5 ohms resistor and the 0.4 ohms resistor. The one that is giving the load is short circuited. It's more like you are standing here to view it. If you view it now, you see that this is wire. This wire has no use. It's the same thing as saying if I clean this wire that is here and I clean this wire that is here, you see that what I have is simply something that is in series. So the R equivalent, that is the Rn, is simply going to be the same thing as saying 0.5 plus 0.4, and that should be 0.9, right? So 0.5 plus 0.4, so 0.9 ohms. So this is your 0.9 ohms. So assuming they now ask you maybe to find the current in this particular one, maybe they ask you that as you have your load now, it's different from when they say the Thevenin current that we've gotten. As you have this load now, and you have this Thevenin's current, maybe they come and tell you find the current in this road resistor. Let's say you are given this Norton circuit and they ask you to find the current in this. So the video is getting long. Check out the next video so that you see how to find current in this load resistor. Or remember, this is Norton Rn. Maybe instead of doing this, they ask you to find the current in this Norton's resistor. Whichever one they ask you, in our next class we'll find it. We'll show you how to go about it. So subscribe to the channel.